Good morning. So this will be a continuation from the last video dealing with essentially electrical theory basics. So um, let's go here. Let me see if I can share my screen with you guys real quick. On my glasses here. There we go. Put this up here out of the way. All right, so let's see if we can identify the units, current, voltage, resistance. We're going to go through this, and it's going to take us a little longer than probably you'd care for, but I really want to make sure that we truly have an understanding or a concept of the difference between voltage, current, and resistance, and how all that plays a role or a part in what we're doing here. So, or what we're trying to learn. Let me grab my glasses real quick. Okay. All right, here we go. All right. So electrical charge and current, talking about the movement of electrons, right? We talked about how electrons move freely through conductors. All right, so let's see here. So they're saying this is a battery cell, and as the electrons move, it moves from negative to positive. Just kind of a constant cycle there. Now it says the ability of change or charge to do work is called the potential. The sum of the electrical charges in a field is the electromotive force. So EMF, electromotive force, is what we call voltage. It's the pressure. It's what pushes those electrons. Imagine filling a container with like an air, and as it gets bigger and bigger and bigger, that pressure would be the representation of voltage. Just like if you were spraying the flowers with a water hose with a nozzle, the amount of pressure inside that hose would be the amount of, how much water is coming out of it would be the voltage. So just kind of because you can't see the electrons, so that's why it's really hard to kind of representation. So just give these little metaphors like water in a water hose. So like I said, it's the amount of pressure, how much push is what we refer to as the voltage. And we're going to use, I'm going to teach you a little bit of Ohm's law here. So we'll go from there. We're not going to test on it. We're just going to learn it, right? So expressed as the equations as E. Electric charge is measured in coulombs. All right. So the actual charge itself, this is how we measure it. We have a substance, we have to measure its quantification, and in this case, the electrical charge itself is actually measured in coulombs. Now, a battery creates an electric charge by chemically producing free electrons at its negative terminal. And as it's introduced to a load, something needs to be used, power, is being exerted, then it's the electrons start flowing in from negative to positive. Now, current is flow. Current flow is measured in amperage, and it's the intensity of the current flow is represented by the equations by the letter I. Trying to see how I can best express amperage. So if the pressure itself of pushing the water out is voltage, it's the water itself that's being pushed would be the amps. If I barely crack a water hose on, water's coming out, but it's a very limited amount because there's no pressure. There's still water, so we'd still have amps, but it's just not enough pressure to really push and meet the needs of the load. So that's why we increase the voltage. Therefore, we can get the amperage to come out more easily, and then of course the load is accommodated. It's kind of a raw analogy and not the best one, but just to kind of give you guys a mental picture of how voltage and amperage work together to produce the power needed to run a motor, to power a light bulb, to operate a telephone or a TV. Okay, now we're talking about resistance. We talked about resistance last time, and we decided that resistance is the opposition to current flow, right? It's just like I mentioned the other day. Is the last video is if I grab someone's shirt tail and I tell them to run as hard as they can, doesn't mean I'm going to stop them from getting to that point. It just means I'm going to impede them from getting to that point. So that's what resistance is. It's the opposition to the current flow. It is measured in ohms. This is the symbol. It's the omega symbol, and represented by the equations by the letter R. The hotter a wire, the greater its resistance. Now, what they're saying is, let's say, for example, if I'm putting a battery to, let's say, a large piece of copper, like the copper that we typically use, that you guys have been putting your devices together with, then it's not going to get real hot, is it? You might feel it get warm, but if you just take the piece of copper and you attach it to both sides of the battery and you just feel the copper, you're going to say, oh, it might be getting pretty warm, because as the electrons flow through it, the larger the copper, the least resistance, right? Now, if you do take a paper clip and you do the same thing to it and you touch it, it's going to get pretty hot because the wire is thinner. It's made of maybe a poor conductor. So the electrons are fighting hard to get through that conductor. It's still, the requirement's the same. It's going to push those electrons through it. And it depends on the size of the conductor, what the conductor is made of, whether or not it flows freely. If it flows freely, it's not going to get near as hot because it's operating at normal capacity. It's when you impede it or you create a stressor for that path is whenever it starts to get hot. All right, so we're going to move forward. All right, so this here is Ohm's law, okay? And we're just going to cover it right here. And I'm going to go through some examples and stuff like that. But like I said, I'm not going to test you guys on Ohm's law. I may ask you, what is Ohm's law? And you may have to tell me that it's got voltage, it's got amperage, and it's got resistance. And I may ask you what the letter representing Ohm's law, for example, E, electromotive force for voltage, and then you get I, intensity for amps, and then R, resistance, and it's measured in ohms, right? So these aren't crazy hard, but maybe even be a good idea to even pause it and say, okay, let me write this down. Ohm's law, it's E over IR, and we're going to talk about how this works here in just a second. Now, Ohm's law defines the relationship between voltage E, current I, and resistance R. Now, the formula itself can be rearranged to find any of the three values. For example, if I'm looking to find what is the amperage, then I'm going to divide E over R. So look at the representation right there. Look at this right here. If I just say, okay, this is what I'm looking at, and I need to find I, well, the math problem's already there. E is already sitting on top of R. We already know it's a division problem. We know that we're going to have to divide voltage by resistance. Let's say, for example, we're trying to find voltage. What is the voltage of this particular question? So we're going to see that E is over IR. So I can look at it, says I is sitting right next to R, so it's I times R. If I need to find the value of resistance, well, look, it's the same thing, math problem, division. E is sitting right on top of R, or E is sitting right on top of I. So it's just like the formula shows right there. So it's not hard. It's 3, right? I'm not asking you to learn the power wheel at this point. Power wheel's got, I think, 12. So just focus on the Ohm's law. Take a moment, draw a circle, draw your E, I, R, take care of all that. And then as we move through this, just kind of work it with me, and just kind of just, pause the video for a second, scratch it out, try to make your brain think beyond this confusion. And it's okay if you don't get it. It's okay. I've got grown adults that struggle with this. So, all right. That video is done. So let's move on here. Thank you for your patience, guys. Should have had that one up already. All right, so let's stop sharing that. Let's share this video. Go to here, session 3. There we go. Okay, we've seen this before, right? This up top. Electrons are flowing from the negative through the switch, through the conductor to the lamp, and back to the light or to the battery, right? That is a series circuit. Everything is linear. See how it goes one wire from the negative, one wire to this. The switch does nothing more than open and close a circuit. That's it. Nothing magic, nothing special. It just opens it and it closes it. Closes it means it turns it on. It bridges that gap, right? And then as the electricity continues to flow through, goes to the light bulb, travels through the light bulb, and then all the way to the positive. So when you put a positive and a negative, what do we say would happen if you touch them together? Right? Well, in a vacuum, it doesn't explode, just like space, right? If you were to set off a bomb out space, it wouldn't explode because it has to have oxygen. It has to have that ability to combust. Well, a light bulb, same way. It's got a vacuum. So when you take those two voltages or a different potential and you touch them together in there, it just gets hot. It gets super hot. So that inside that light bulb has a piece of wire, and that piece of wire is called a tungsten. And that tungsten wire is built of such density that it doesn't just incinerate. You know, when you take two hots and neutral and hot, and you touch them together, right? Well, in this case, that wire is so strong, and it's like I said, it's made of tungsten, and it gets super, super hot. And then instead of blowing up, it gets bright, right? So that's how a light bulb works. It just illuminates. Now, as soon as you crack that bulb, pops it just like that, done. All right, let me see if I can back up real quick. All right, this down here is what we call a schematic diagram. This is what we're going to start working here today. So I want us to take a moment and pause the video, and I want us to sketch this out real quick. Do the best you can. I'm not looking for artistic here. I'm just looking for a rectangle showing a battery source, showing a switch with a toggle, and then of course you got your light, which is your load, right? It's what's using the electricity. So I want you to draw that for me right now. And then we're going to go through a couple more, talk about symbols and stuff. All right. These are some standard symbols. I'm not asking you to memorize them. Just look at them for a second. Just look how the symbol kind of matches, but does it really? Like, let's look at generator AC real quick. See how it's got the symbol and it's got the sine wave right there? Well, that sine wave represents alternating current. So there's that. Of course, battery. See if ground's on there. Yeah, ground. Definitely want to know ground. Want to know battery. Want to know generator. Lamp, I guess. All right, so we're going to move on. So these are different types of resistors. Now, in the residential career field, you're not going to run into these very often. The only time you'll probably ever run into them is whenever you run into like a security system, and they require in their piece of system that there be a resistor of whatever it is, and then you have to know what type of resistor to install in that system, because there's resistors in a security system determines on how sensitive something is. If you allow a certain amount of vibration, certain amount of sound, certain amount of whatever, or it then it's going to send that signal through faster than you want it. And every time a bird lands on your windowsill, you're getting the police running to your house thinking someone's breaking in your house. So that's why sometimes resistors are super important. But be honest with you, I haven't run into it, but just a couple of times. I think maybe one time I had to deal with it with when I was wiring some rental condos down on the beach, and they required it as part of their fire safety stuff. So other than that's the extent of it. Commercial end, you probably may have to look at these a little more, especially when we're dealing with fire systems and fire suppression systems and detection systems and security systems and stuff like that. So, but once again, we just don't deal with them very often. These are more of electronics career field, and we're not doing electronics. So some of you guys who have been working some of the STEM programs here at the school, maybe you're more familiar with the resistors than we would be in, building career fields. So anyway, resistors typically made of nickel resistance, wire covered in porcelain. Fixed resistors are the most common, but variable resistors are also available. You can look at the different color bands, and we'll go over that here just briefly, though. All right, here's some symbols used for variable resistors to include a rheostat, such as a dimmer. Rheostat is an adjustable way to adjust the amount of voltage running through something. And you may have seen those, like, for example, you walk in a room, you'll be able to dim a light. That's a variable resistor. Essentially, you're just resisting, you're adjusting the amount of voltage flow based on the level at which if you have it wide open, around 120 volts. If you're bringing it down, you may bring it down to 40 volts, which gives that light just a little bit of illumination. So now the resistance is adjusted using movable contact. And of course, these are the colors that we mentioned a while ago. You can pause the video if you need to. This is non-testable, by the way, as far as I'm concerned. Okay, so now we're going to talk about circuits. Let's look at this very first one right here. This is your standard series circuit. I have a conductor leaving my negative terminal, going up. It hits a load, a resistor, whatever you want to call it. We're going to call it a resistor just for now, only because that's what the book is calling it. It can be a load, it can be a light bulb, it can be an LED, it can be whatever we want it to be. But it's what literally impedes or uses electrical current. Now, the reason they call it a resistor because we want the same amount of voltage and the same amount of current to go all the way through the circuit. We don't want to use or consume current in this. We want to make sure that it's flowed just for math purposes. Okay. Now, in a parallel circuit, as you can see, it has multiple paths here. As it goes up, it's actually coming up. It gives me an option at this point, right? I can go right, or I can continue to go forward. And then I can go this way and then come back around and go that way, right? So in this situation, I have 3 paths that I can go through, right? I don't have to, if this lamp blows, these 2 still work. Now look over here. If this lamp blows, then this light won't work because I can't point at it with my hand and illustrate. But imagine this. We're going to say this is the resistor. If this blows, the bridge is open. Electrons can't flow from here to here if this is blown, right? So therefore, the circuit's dead. Now, over here in the parallel circuit, it gives me an option. Let's say that R2 right there, let's say it blows up. Pops, guys, goes away. I can still operate on R1 and R3. Let's look over here on series parallel. Now, in this situation here, you notice how we have both. Now, let me ask you this. What happens if this one blows? That one blows, they all go out. Well, let's say this one's a hardy one. It doesn't go out. But now I have choices. But what happens if this one blows? They all go away. So This is like I said, more we used to call it complex circuit, but they've since stopped and started it's series parallel circuit. So yeah, these types of determine the method used to calculate resistance. And we're going to talk about the math part later. So we actually have to measure our devices, measure our voltage, measure our current and stuff like that. So we have specific meters sometimes that are designed for specific tasks. Most meters we use today are multimeters. They have variable uses, right? We can check current, we can or amps, we can check voltage, we can check resistance. Some of them even can check temperature, right? So this one right here is a digital. Digital means it has like a display right here. Analog means it has that needle that bounces back and forth. These are still out there, some of the old time guys. And if you ever go to like a Radio Shack, if they even find anything like that, sometimes even at Ace Hardware, you can go in and you can find those little analog meters and they work just fine if you can be patient enough to see what, find that line. This one here is super easy. You just, as soon as you pop it in there, you put the selector level to what you want, and then it reads whatever you're looking for. All right, this is a clamp-on ammeter. So you notice how it's got this ring right here. This is what determines when we clamp it around it. It tells us how many amps are actually drawing through a conductor. One of the reasons we don't clamp it around two conductors, one is because it gets confused because it has current flowing one direction and it has current flowing back another direction. So it gets confused on what's coming and going. It gives you a crazy reading. We don't put it around two conductors feeding into a building because it doesn't understand that either, because first of all, they're out of phase. Second of all, it's not a calculated because each line isn't balanced. So that's why we use one conductor. If you clamp it around one conductor, it'll tell you how much power is being used on that one conductor. So it says a clamp-on ammeter is used to measure the current through a conductor by clamping the jaws of the meter around the wire. The magnetic field created by the current in the conductor is then measured by the meter. This is a perfect illustration right here of how it's used. Do not use a clamp-on ammeter with dirty or misaligned jaws. Use the ammeter on only one conductor at a time. This is right here showing how to do an ammeter in line. Now, this is DC, okay? DC. I can't tell you how many times I hand out these meters to young men and women, and next thing you know, they blow the little fuse inside because first thing they did went to their outlet and they tested it. Our outlets are on alternating current. These type of meters right here that deals with the leads, that is for direct current, and there is a maximum ampacity. It's like a 10 amp or 0.10 or whatever it is. I can't remember, but if you look at it and you take that selector lever and you say, okay, I want amps, you best be testing something that's attached to a battery. If not, you're going to end up blowing up blowing the fuse inside the meter. So that's why I called it inline ammeters, connect in series with a circuit, and are much less common because they require the circuit to be open. All right, so we measure voltage. Voltmeter is connected in the parallel with cross the component in the circuit, tested to check whether the voltage. So when we check voltage, black typically goes to negative, and red typically will go to positive. Now you notice the illustration here. It really doesn't matter. The only difference that's going to matter is you have to put the red on the, it doesn't matter, to be honest with you. If you show a negative, if the numbers that you're doing, like for example, you're doing a 12-volt battery and you put it on there and it shows you negative 13, just turn your leads around. It's reading backwards. So this illustration is very backwards because typically black goes to negative, red goes to positive. So not real sure why the illustration shows that. Okay, measuring resistance. Resistance is measured using the ohm meter with the power shut off. Okay, if there's voltage running through there, you're going to mess up your meter, or it's going to get a horrible reading. You're not going to understand what it's saying. Ohm meters can be used to check the resistance of a motor winding and to check their electrical continuity. And we're going to talk about continuity. I don't know I have time right now. I've only got a few minutes before I have to go to work. But I just wanted to, yeah, we'll talk about how to, what continuity is and how it can affect the flow of electrical current through the circuit. This is a continuity tester, just making sure that from point A to point B has no problem. Okay, that's essentially it. You don't have a break in your wire. That's we use most automotives. Your parents may have these in their vehicle. It just says, okay, do I have a hot and a negative? Do I have a hot and a negative on a circuit? Electrical power, we talked about 1 volt, one times 1 ohm equals 1 amp. Ohm's law, right? Volt, amp, ohm. All right. Oh, there's the power wheel. Not gonna make you know this, but just understand that wattage, volts times amps equals watts. Watts is the measurement of power. That's how we determine how much power something's using. We use wattage. So power is wattage, right? Wattage is volts times amps. So that is, if you get nothing else out of this, that's the most important thing right there. And like, so we're going to go through the power wheel at some point, just not right now. All right. So in a nutshell, I've just walked through, and I know I went through it really quick, and we are going to come back to it. Unfortunately, my time is very short. I've got to actually run to work right now. So yeah, so tomorrow maybe I'll have some equations, some math, some little problems or something we can work on. So anyway, hope you guys have a wonderful day.